Okay, so today I'm going to be doing an example of a statically indeterminate problem. And we have this rigid body A, B, C, D that's bolted at C, D. And we also have a pin at B. Okay, so the given things are the diameter CE, diameter DF, and the modulus of elasticity for aluminum. They want us to find the forces in member CE and the forces in member DF, and also the uh, the deflection at point A. So first step is to draw a schematic diagram and label your forces. And remember that B is a joint, so that should have two forces in the X and Y direction. Now, sometimes people get a little confused. You could direction your arrows, your vectors any way you want. For instance, you could make them all going up. But the reason why I chose these ones specifically is just by analysis. So suppose you have like an invisible line right here, right? And if I force this and I'm pinned at B, when I push this down, this will push up, this will push up, and B, this will want to have the tendency to push up, but the forces, the internal forces, will act downward to prevent it from moving up. Now at B, and when I push down at B, it would have the tendency to compress B. So the internal force would want to counteract that natural tendency to compress the pin. Okay, so that is the reason, but either way, if we get it right, we get it right. If we get it wrong, we'll just have a negative. So it's no big deal. So now that we have our schematic diagram, and we have labeled our positive y and our positive x. Now we could do we could start off with our step 2 would be to create our static equations. Should be 3 equations, right? The sum of the forces in the x direction is equal to 0. Therefore, Bx is equal to 0. And the sum of the forces in the y direction is equal to 0. So therefore, we have negative 10 plus by minus cy minus dy is equal to 0. So therefore, we can conclude that by, let's do it down here. By minus cy minus dy is equal to 10. And this right here would be our first equation. We'll call this one our zero equation because it really doesn't help us much. So now let's do the sum of the moments at some point is equal to 0. Now we have to choose this point carefully, right? What is the question asking us? The question is asking us for the internal forces of CE, so this point, and DF, this point, right? And of course the deflection, but the deflection would be at this point. So what other point could we take the moment at that involves all these other forces? Well, we'll take it at B, right? Because they don't really care about the forces at B. So let's take the moments at B, and we'll have positive 10 multiplied by the distance 18 inches. So 18 inches. Let's put the units. Kips, 18 inches. And the moment given by C is going to be clockwise. So that would be a negative CY multiplied by 12 inches, right? That's this distance right here. And then another negative moment, dy, and the distance from D to B is 12 plus 8, which is 20 inches. Okay, so do we have any other forces? No, we don't. So this is equal to 0. You can get that 12, 20. So let's bring CY. So we'll get 12 CY plus 20 dy is equal to 180. And we have to remember that we are in kips. And this would be equation 2. So now we are done with, we have used up all of our static equations, and we have to look, how many unknowns do we have? We have 1, 2, 3, and 4. So we have 4 unknowns, and we have 3 equations. So therefore, statically indeterminate. Yeah. It's greater than. All right, so now what do we have to do? We need to come up with another equation. And this is the reason why we are learning strength and materials, is because now we can use the equation for deformation. So this would be step 3. And this is strengthen materials. Deflection equation. So there's 2 deflection equations, right? But we don't have no temperature change, so we could say that the deflection formula, or the deflection is equal to PL over EA. And what's going on here? Why does it cover? There we go. Oh no. There we go. Sorry about that. Okay, so that is our formula. So now I'm going to do a geometric diagram of these schematics. Copy, paste. Okay, let's take off some things. Let's leave the y-axis. Yeah, we'll leave the y-axis. We'll take off these. Don't need these because we're not doing any forces. All we're doing is geometry. Okay. So let's take a look here. This rigid body is pinned at B. So that means as this rotates down, this rotates up, and it has its natural tendency to move like that. Okay. So I'm going to do an exaggeration line, but we know that the deflection will do something like B is actually shorter, 2A. So let's move B. Let's move B right here so we can kind of get a feeling of what's going on. Okay. So this is the deformation, the natural tendency to deform, right? So let's get A's right here. what's going on. No, do not want that. Deflection at A. Deflection at C. And deflection at D. Okay. And now we need to establish the relationship. So using, actually, let me write the dimensions right here. That's going to be important. 18, 12, 8. So this is 18, 12, and 8. Okay. So using similar triangles for C and D, meaning we are going to use this triangle right here. Well, that didn't make a triangle, but you get the point. It's this triangle right here, okay? That triangle, along with this triangle, will be DC as a distance divided by this length right here, which is 12, is proportional or equal to displacement at D over D is the big triangle, so it's going to be 12 plus 8, which is 20. Okay. All right, so if we bring everything to one side, we'll have displacement at C over 12 minus the displacement at D over 20 is equal to 0. Now we have found our third equation. Now let's see what happens here. So let's do use this formula up here, PLEA, right? So the displacement at C would be CY, the length of member C, right? The length of member C, let's see what it is. The length of member C is this length right here, right? Which did they give us? That length? Yeah, it's 24. Yeah, it's 24. So this length is 24, and we're in inches, divided by PLE. What is E of those screws is 10 to the 6 times 10 to the 10.6 times 10 to the 6 psi. But actually, we could divide it out because since they're both going to have the same material, we'll just keep it at E. Let's see if the area is going to be the same. The area, nope, the diameters are different, so the areas are going to be different as well. Okay. And remember that the area is the not the not this area right here. It would be the area of these tubes, which is these are circular tubes with a diameter d. Okay, so for CE it's 1/2. So what is the area of a circle? Is 1/2 pi r squared. Let me just double check that. I always forget these. Oh no, it's just pi r squared. Sorry, pi r squared. And the radius of CE is 1/2 of 1/2, which is 1/4. So then we could put 0.25 squared. So that's just pi r squared minus dE. Oh, and then remember we have 1/12 being multiplied by it. And then we have 1/20th dy. What is the length of? The length is 30. 30 inches divided by E. Remember, it's E of aluminum. And then let's see what this is, pi, and let's see what R is for D. R for D is 3/4, which is 1/2 of 3/4. And 1/2 of 3/4 is 3/8. So we'll get 3/8 in decimal, which is 0.375. Okay, and that's squared, and this is equal to 0. So of course, when you cancel everything out and you simplify, you end up getting that CY minus 0.333 of dy is equal to 0. Now this is the true equation number 3. So we'll just put like equation number 3 star or something like that. Okay. So now we have, let's go check out our other two equations. We have by, cy, dy, cy, dy, and cy, dy. So we'll use these two. We'll use copy equation 2. So we'll do, see what step this is. Step 3. Okay. Step 4. Let's solve for unknown. Okay. So we'll take equation 2, equation 3, right here. We'll solve this system of equations. We can use matrices. We can use system of equations. I'll go ahead and let you guys take care of that. But this will end up being CY is equal to 2.4 0.50 kips, and dy is equal to 7.50 kips. Okay. So we'll put these solutions all the way to the side. And we could say that based on Newton's law, since this has a reaction here, Cy, F of Ce would be equal to Cy, and F of dF is equal to dy, right? So when I say that Cy and dy is 2.5 and 7.5, what I really can say is this is F of Ce and F of dF. Okay. So that's what they wanted to solve originally. So these are done. These are done. Now we need to find the the deflection at point A. So let's go back down to our geometric diagram. Okay. Now let's try to find the relationship between dA and DC or DD. We could use either one, but what I want to do is I'm going to use the relationship between dA and DD. Okay, and to do that, I need to find a proportion, them in proportions. Okay, so notice if I take a copy of this and I paste it here, right? And then I draw an intersection where this is 90 degrees. And I'll name this, this would be, let's just call it Y, okay? Well, there's a proportion of dA over 18 is proportional to Y over, let's see, 18 plus 12 plus 8, 18 plus 12 plus 8, that's 38. But there is also another proportion, right? There's another proportion. There's this proportion right here. Look at this triangle and this triangle, okay? So if we use that proportion, we could say that Y over 38 is also proportional to the displacement at D, or the deflection at D, divided by 12 plus 8 is 20. So therefore, we can conclude that dA over 18 is equal to D at 20. Okay. So the deflection at A is equal to the ratio 18 to 20 of the, I keep saying the different thing, deformation, sorry, deformation at D. So the deformation at A is equal to 18 over 20 of the deformation at D. And we can find the deformation at D. So this is 18 over 20, and the deformation at D would be FDF L divided by L of DF, E aluminum, and A of member DF, which is equal to, we'll do it down here, 1820 times, let's see, DF, we found it over here, 7.5 kips. The length, DF, is 30 inches divided by E, which is 10.6 times 10 to the 6 PSI, multiplied by the area, and the area of ADE, let's see, DF, sorry, DF is, okay, the diameter is 3/4. So we said right here, I think we said is pi 0.375 squared. Pi 0.375 squared. So when we calculate all this, we'll get the deformation or the deflection at A will be equal to 43.2 times 10 to the 3rd inch. We can move this bad boy right here and put a star around it so we can bring some attention. And we have solved this problem here. See how I put my my answers over here on the side? It makes it really clean. Looks really nice. So that's how long it took.